In this tutorial, we are going to talk about something called chemical periodicity. First, we're going to talk about the history of the periodic table, at least briefly, and then we're going to talk about how it's organized, and then we are going to talk about the elements and their reactivity. Okay, this is Dmitri Mendeleev. He is credited in a lot of textbooks for developing the first periodic table. And he did this by putting the elements into in order of increasing atomic mass. And he also arranged the elements into groups with similar properties. All right, so this is what his first periodic table looked like. And you can see that he has groups. So the columns going up and down are his groups. And that the elements are ordered by increasing atomic mass going across the periodic table. So the issue that he found when making, well, something that's really cool when he made the periodic table is he noticed some inconsistencies, or he noticed that there were gaps in the periodic table. So places where there were elements that should be there that we don't know about. And so he actually left gaps in the periodic table and was able to actually write down what the properties should be of those elements that had yet to be discovered. And that's pretty cool. And then the other thing that he did is he noticed that there were some inconsistencies with, say, mass, atomic mass and properties. So the best example I can give you on the periodic table is if you were to look at element number 52 and number 53, iodine and tellurium. On the modern periodic table, their atomic masses do not go in order. Tellurium comes first, and iodine comes second, and tellurium weighs more than iodine. And he thought those should be switched on the periodic table because they fit better into their little groups when he didn't arrange them by increasing atomic mass. So he was able to even foresee that, like, maybe sometimes arranging them in order of atomic mass isn't the best. But that was all he had to go on. Okay, so then in 1913, Henry Moseley was able to use X-ray diffraction to determine the atomic numbers, or the number of protons of the known elements at that time. And because of that, we were able to further organize the periodic table by increasing atomic number instead of increasing atomic mass. And that, ended up looking like this. So here's our modern periodic table. And in our modern periodic table, we organize the elements by increasing atomic number. So 1, 2, 3, 4, all the way up to in the most current periodic table, 114. And this led to the periodic law. The periodic law states that when you arrange elements by increasing atomic number, you will start to see these patterns develop or a repetition of physical and chemical properties. And we're going to talk more about that in part 3 of this video. First, though, let's talk about how the modern periodic table is actually organized and all the wonderful ways it's organized. Okay, so the modern periodic table is organized in a couple of different ways. So first we're going to talk about periods and we're going to talk about groups. So periods are the rows going across. So there are 7 periods on your periodic table. And the elements in a period have one thing in common. They have the same number of energy levels, and that's about it. So if you were looking at your periodic table and you were looking across period 3, so period 3 starts with sodium and then has magnesium and ends up, going all the way through argon. all of these elements in this periodic table, or in this row, have 3 energy levels. So that's basically what the elements in a period have in common. All right, the vertical columns going up and down, these ones are called families or groups. I prefer the word family, although I will use both interchangeably. And the reason why is because the elements in a family have similar properties, both chemical and physical properties. So your families are numbered across the top of your periodic table. And they go from 1 all the way to 18. Now, this periodic table, this picture that I'm showing you is abbreviated a little bit. It's missing some stuff in the middle. So I'm going to show you the real periodic table. All right, so here's the real periodic table, and you can see that it's numbered across the top, group number 1, 2, 3, all the way over to 18. So there's your group numbers. And the groups have names. So group or family number 1 are called your alkali metals. Group number 2 or family 2, these are your alkaline earth metals. And this whole group in the middle, families 3 through 12, these are called your transition metals. And then you've got group 13, 14, 15, and 16. They have names, but you don't need to know them. And finally, you have group 17. These are called the halogens. And group 18, you may remember from class today, these are your noble gases. And in a minute, we're going to talk a little bit more about these groups of elements. But first, let's talk about metals, nonmetals, and metalloids. So you may or may have not noticed that on your periodic table, there is this line that looks like a stair step. That stair-steppy line actually separates types of elements, and there are 3 types of elements. There are the metals, the nonmetals, and the metalloids. On the left of your stair-steppy line, not including hydrogen, you have all of your metals. So all of your elements that are in blue on this periodic table, these are your metals. And then all of the elements that are in yellow or whatever color this is, this kind of orangey color, these are your nonmetals, including hydrogen. And then all the elements that you see in green right here, these are your metalloids. And you may want to color code them. So metals are on the left of the line, nonmetals are on the right side of the line, and then elements that are actually touching the line except for, I want to point out, aluminum and polonium. Oh, actually, polonium, I guess now is considered a nonmetal, so everything except for aluminum are considered your metalloids. You need to know the properties, or at least the physical properties, of metals, nonmetals, and metalloids. So properties of metals. Metals tend to be solids at room temperature, except for mercury. Mercury is the only one that's a liquid. If you polish them, they tend to be shiny. They conduct electricity and they conduct heat. And they are malleable, which means they bend without breaking. And they can be stretched into wires, which is called ductile. Nonmetals tend to be they're kind of all over the place. Some are solids, some are liquids, and some are gases at room temperature. They aren't shiny. If they're a solid, they tend to be very dull. They do not conduct electricity very well, except graphite will sort of conduct electricity. Graphite, by the way, is the stuff you find in your pencils that we call lead is really graphite. They do not conduct heat. They break easily, so they're very brittle, and you cannot stretch them. So metalloids, the thing with metalloids is the reason that we call them metalloid as opposed to just straight up metal is that they have properties that fall somewhere between metals and nonmetals. So, for example, silicon. Silicon is a metalloid, and silicon is a semiconductor, which means that it doesn't fully conduct electricity. Its electrical conductivity is actually adjustable or changeable depending on how hot you get it, which makes it perfect for use in like computer technology, because you can adjust the rate at which it conducts electrical conduct or electricity, where you can't do that with a metal. It happens to be very brittle. So when you hit it with a hammer, it's not, so we're talking specifically about silicon. It doesn't break very easily, or sorry, it doesn't bend, it's not malleable. But it is super lustrous or shiny, just like a metal. So it's somewhere between a metal and a nonmetal, and all your metalloids are kind of like that. They don't have the same exact properties as silicon, but their properties are not 100% metal and they're not 100% nonmetal. So we kind of make their own category and call them metalloids. All right, the last topic that we're going to talk about is why the periodic table is arranged in groups, or like how did we come up with these groups, right? We said that, for example, group number 1 is called the alkaline metals, and group 2 is the alkali earth metals. And what is it about them that makes them similar? So we said they have similar properties. If you remember that elements in a group have very similar properties. So we're going to look at, see, the alkali metals. These elements all have similar properties for a reason. So lithium, sodium, potassium, rubidium, cesium, and francium. I'm not going to write all of them. Why do they have similar properties? Well, I'm going to show you why. If you're going to do the electron configuration for each of these elements, this is what you would get. And you'll notice that each one of them ends up with their outermost energy orbital having only one electron. We call that electron, the outermost electron, a valence electron. So that's the word for an outermost electron, valence electron. So each of these elements in group 1 have one valence electron, which means that they are going to react very similar to one another. So we're going to start talking about chemical reactivity and what it is that's actually happening, and it has to do with the valence electrons. So they're very similar because they have the same number of valence electrons. And you could do the same thing for family number 2, the alkaline earth metals, and you'll see that their outermost orbital or energy level has 2 valence electrons. So VE is valence electrons. So they're going to react very similarly to one another. So that's why they're in a family together, because they have very similar electron configurations. Or you could look at your halogens. I only did fluorine and chlorine in this row. You could go all the way down the row and do all of them, but I just did these 2. But you'll notice that they also have very similar numbers of valence electrons. We want to look at the whole energy level. So the entire second energy level of fluorine has 7 valence electrons. And so does chlorine. Its third energy level has 7 valence electrons. So you'll notice that these elements have they have similar properties when they're in a family because of their electron configurations. In fact, I'm going to tell you a little bit of a secret. If you look at the family number is going to help you determine the number of valence electrons. The only families those don't work for are your transition metals. Those ones are funky, and we'll talk about them later. So remember, we did the electron configurations for all the elements in group 1, and we saw that they all had 1 valence electron. So group 1, they have 1 valence electron. Group 2 all had, they're right here, right? They all had 2 valence electrons. Group 13 is where things get a little bit funky. Group 13, they all have 3 valence electrons. Group 14, they all have 4 valence electrons. Group 15 all has 5 valence electrons. Group 16 all have 6 valence electrons. And as you saw over here, group 17, right, the halogens, they all have 7 valence electrons. So how many valence electrons do you think are in the noble gases group 18? Hopefully you said 8 valence electrons. So that concludes my video on chemical periodicity.